Alright, let's go. Number 10. The observer boundary. In the late 1970s, a physicist named Bryce DeWitt was not trying to rewrite the nature of time. He was working on a unified approach to canonical quantum gravity, specifically trying to understand how the Wheeler-DeWitt equation behaved at the boundary conditions of spacetime. Routine theoretical housekeeping. The kind of paper that gets read by 12 people and cited by 40. What fell out of his calculations was something he spent the next 2 decades trying to qualify. Every physical theory we have, every equation in quantum mechanics, general relativity, thermodynamics, classical mechanics, was written by observers inside a 3+1 dimensional spacetime. 3 spatial dimensions. 1 time dimension. All our physical laws describe relationships between events as experienced from inside those constraints. They are not universal laws, they are local laws. Laws of this particular vantage point. This is not philosophy, it is a formal limitation embedded in the mathematics itself. Here is the problem. The 5th dimension, in virtually every framework that includes it, Kaluza-Klein, braneworld models. M-theory would permit an observer with access to it to perceive our entire temporal axis the way we perceive a spatial axis, not moment by moment, all of it. Simultaneously, your birth, your death, this moment you are watching this video, not a sequence. A shape, a static object extended through a dimension called time that this observer perceives the way you perceive the length of a table. There is no theoretical framework for what that observer would actually experience. Not a speculative gap, a formal one. John Wheeler at Princeton explicitly noted in his 1983 work on participatory universe models that our theories offer no vocabulary for an observer outside our dimensional set. We have not avoided this question. We have been structurally incapable of asking it correctly. Every explanation proposed collapses. You cannot extend human perceptual categories to a 5D observer because those categories are generated by a 3+1 nervous system. You cannot use physics to describe an observer outside physics as we have formulated it. You cannot even use the word experience without begging the question. Your life, from that vantage point, is not a story. It is an object. And we have no idea what it looks like. That leaves us with a more ancient question, how we know extra dimensions exist at all. The answer begins here. Number 9. Dimensional resonance frequencies. In the mid-1990s, Joseph Polchinski at the Kavli Institute for Theoretical Physics was not hunting for ghost particles. He was working out the precise role of D-branes in type 2 string theory, technical objects that describe the endpoints of open strings. The mathematics required him to calculate what happens to fields at the boundaries of compactified extra dimensions when energy levels match specific thresholds. What his equations produced was an output he initially filed as a formal artifact, a resonance condition. M-theory, the 11-dimensional framework that extends string theory, predicts that the compactified extra dimensions have natural resonant energy scales. They are not passive containers. They have frequencies, the way a guitar string has a natural vibration. When a particle's energy matches one of those frequencies, the mathematics allows something unusual. The particle can interact with the geometry of the extra dimension directly. The prediction is this. Particles at those specific energies would appear to emerge from vacuum, interact once with other particles, and vanish back into vacuum. Not violate conservation laws, just produce interaction signatures that look, from our dimensional vantage point, indistinguishable from quantum fluctuations. Random foam. Background noise. In 2003, researchers analyzing data from the Tevatron Collider at Fermilab, led by Bogdan Dobrescu and Konstantin Machev of the University of Chicago, published a paper in Physical Review D identifying a class of anomalous collision events that produced unexpected energy signatures. Every conventional explanation was tested. Detector artifacts, ruled out by redundant sensors. Rare but known particle decays, the decay products did not match. Statistical noise occurred at higher than Poisson frequency in specific energy bands. The paper proposed, cautiously, that dimensional resonance was a candidate. Nothing in the standard model of particle physics predicts the patterns. The standard model has survived every precision test in history. Its failure here is not its weakness. It is a signal. What is disappearing during those events and where it is going is still an open question with no agreed answer. Number 8. The time dimension collapse. Claude Itzikson and Jean-Bernard Zuber were not cosmologists. They were mathematical physicists at the Saclay Research Center in France, working in 1980 on matrix model techniques, abstract algebraic tools used to count specific configurations in two-dimensional quantum field theory. Their paper was technical, abstract, and made no cosmological claims whatsoever. The conjecture that now bears their names emerged as a side consequence, a structural implication that neither of them initially foregrounded. The standard cosmological picture assumes time has always been exactly what it is now, one dimension, asymmetric, moving forward. But there is no fundamental reason in quantum field theory why this must be so. Some theoretical frameworks, notably work extended by Itzhak Bars at the University of Southern California, beginning in a 1996 paper in Physical Review D, proposed that the early universe may have contained two time-like dimensions, and that one of them compactified during the cooling of the post-Big Bang plasma, the same way spatial dimensions are proposed to have compactified in string theory. The Itzikson-Zuber conjecture, as extended into this context, implies something disturbing. Universes with more than one time dimension cannot support stable chemistry. The interference patterns between two temporal axes prevent the formation of stable electron orbitals. Atoms do not hold. Molecules never form. Life is impossible, not accidentally, but necessarily. Every proposal for why the second time dimension collapsed has run into the same wall. Anthropic reasoning, the argument that we only observe a single time dimension because observers can only exist in single time universes, is logically valid but explains nothing. It does not tell us the mechanism. It does not tell us whether the collapse was inevitable. It does not tell us whether it was permanent. The possibility that we are inside a collapsed geometry, that the current shape of time is not a given but a result of a transition, is not ruled out. It is simply not understood. If time has a shape that can change, the direction you think of as forward is not a fundamental feature of the universe. It is a phase state, and we have no idea whether it is stable. Number 7. The Hypersphere cosmology. In 1917, Willem de Sitter and Albert Einstein were in direct correspondence over the cosmological implications of general relativity. Einstein was not trying to find the shape of the universe, he was trying to make his field equations static, because the idea of an evolving cosmos struck him as physically absurd. To do this, he introduced the cosmological constant. De Sitter, working independently, found a solution that needed no matter at all, just geometry. The exchange between them produced the first serious mathematical treatment of a universe that was not flat. What the hypersphere model proposes is this: the Big Bang was not an explosion of matter into pre-existing space. It was the three-dimensional surface of a four-dimensional sphere coming into existence simultaneously, all at once. Space did not expand from a point. The hypersurface itself, the 3D skin of a 4D object, expanded. From inside that surface, expansion looks like galaxies moving apart. But there is no center. There is no edge. There is no outside into which the universe is expanding. The fifth dimension, or more precisely the fourth spatial dimension, is the direction the sphere extends in, and we cannot perceive it because we are confined to the surface. In 1984, George Ellis and William Stoger at the Vatican Observatory analyzed the topological constraints this model places on cosmic microwave background anisotropies. The model makes a prediction. At the largest scales, temperature fluctuations in the CMB should show a specific suppression at low multipoles. In 2003, the MAP satellite returned data. The suppression was there. It was unexpected. It remains unexplained by flat universe models. Every competing explanation, a cosmic variance fluke, measurement artifact, foreground contamination, has been tested and found insufficient. The Planck satellite in 2013 confirmed the anomaly at higher resolution. It persists. If the universe is a hypersphere, there is no location for the Big Bang. The event is the surface itself. The question what happened before the Big Bang is not answerable, not because we lack data, but because the question assumes a geometry that the model prohibits. You are not inside a universe. You are on the surface of a shape extended into a dimension you cannot see, whose full form has never been observed by any entity in the history of observable physics. Number 6. The quantum foam connection. John Wheeler was attempting to quantize gravity in the 1950s, not a radical ambition at the time. Simply the obvious next step after the successful quantization of electromagnetism. In a 1955 paper in Physical Review, he calculated what spacetime itself would look like if subjected to the uncertainty principle at extremely small scales. The result was not what he expected. It was not a smooth fabric with quantum corrections. It was a structure he called quantum foam, a violent churning topology of virtual dimensions constantly opening and collapsing. At the Planck scale, 10 to the power of negative 35 meters, spacetime is predicted to lose its smoothness entirely. Geometry fluctuates. Topology changes. Extra dimensions are not fixed structures at this scale. They are fluctuations. They open, exist for a Planck time, approximately 5.4 times 10 to the power of negative 44 seconds, and collapse. The fifth dimension, in this framework, may not be a permanent feature of reality. It may be a fluctuation that's stabilized. In a 2001 paper in Physical Review Letters, Raphael Busso and Joe Polchinski at Stanford showed that string theory's landscape, the vast space of possible vacuum configurations, allows for the stabilization of extra dimensions through flux compactification. A particular combination of fluxes threads the compactified geometry and holds it. Our universe is one of an enormous number of possible stable bubbles in an unstable medium. The disturbing implication is that the mechanism that stabilized our extra dimensions is not known. The specific flux configuration that produced our physical constants, the electron mass, the cosmological constant, the fine structure constant, was not selected by any principle we have identified. Every value of every physical constant is a consequence of the shape in which the quantum foam happened to freeze. You are not the product of physics. You are the product of a particular crystallization of foam, in a specific bubble, out of an uncountable number that formed and collapsed and will never be observed by anyone. Number 5. Graviton escape. Nima Arkani Hamed, Savas Dimopoulos, and Giadvali were not trying to solve the hierarchy problem when they first met at Stanford in 1997. They were working on moduli stabilization in string theory, trying to understand why the extra dimensions in string models remain compact rather than expanding. The hierarchy problem. Why gravity is 10 to the power of 38 times weaker than the weak nuclear force was a known embarrassment but not their primary target. The AD model, published in Physics Letters B in 1998, fell out of their work as a secondary result. The model proposes that gravitons, the hypothetical force-carrying particles of gravity, are not confined to our three-dimensional brain the way all other particles are. Photons, quarks, electrons, the W and Z bosons, all of them are open string endpoints anchored to the brain. Gravitons are closed strings. They propagate freely into the extra dimensions. Gravity appears weak because we are only measuring the fraction of it that remains in our brain. The rest has leaked away into the bulk. This is testable. At sub-millimeter scales, if gravitons are escaping into extra dimensions, the inverse square law of gravity should break down. Force should fall off faster than predicted. In 2020, a precision experiment led by Stefan Schlaminger at the National Institute of Standards and Technology probed gravitational behavior down to approximately 50 micrometers. The inverse square law held. This does not rule out the AD model. It constrains it. The extra dimensions, if they exist, must be compactified at scales below current experimental reach. Every improvement in sensitivity narrows the window. The window has not closed. Every year that gravity behaves conventionally is a year in which its weakness remains unexplained. The most tested force in physics, the one that holds galaxies together, the one that governs the orbit of every object you have ever seen move, may be weak because most of it is somewhere we cannot reach. Number 4. The moduli fields. Brian Greene was not attempting to derive the mass of the electron when he began his work on Calabi-Yau manifolds in the late 1980s. He was working with Ronan Plesser at Cornell, trying to understand a peculiar mathematical duality, mirror symmetry, in the geometry of compactified dimensions in string theory. A 1990 paper in Nuclear Physics B established that physically distinct Calabi-Yau spaces could produce identical string theories. The physical implications were not the point. The geometry was. String theory requires 6 spatial dimensions beyond R3 to be compactified, rolled up into a shape at scales far below the Planck length. The shape of that compactification is described by a Calabi-Yau manifold. Here is the critical point. The shape is not fixed by any principle in the theory, and the shape determines everything. The mass of the electron, the strength of the strong nuclear force, the value of the fine structure constant, the cosmological constant, all of these are not free parameters slotted into physics by hand. They are outputs. They are consequences of the geometry of 6 dimensions we cannot observe. The parameters that describe the shape, the moduli fields, are dynamical. They can, in principle, evolve. A 2003 paper in Journal of High Energy Physics by Shamit Kahru, Renata Kalosh, Andrei Linde, and Sandip Trivedi, the Kilt paper, proposed a mechanism for stabilizing these moduli through fluxes and non-perturbative effects. It is the most cited paper in string theory history. It works mathematically. It has not been confirmed observationally. If the moduli are not permanently stable, if a fluctuation of sufficient energy could shift the Calabi-Yau shape, the physical constants of the universe would change. Not slowly. The electron mass, the atomic binding energies, every chemistry that has ever existed would reconfigure. Not a catastrophe in the conventional sense, something more disturbing. A universe in which the same atoms exist but are now different objects. We do not know why the manifold has its current shape. We do not know if it is the only stable shape. We do not know if stability is permanent. Number 3. Shadow branes. Paul Steinhardt was not looking for dark matter when he began developing braneworld cosmology in 2001. He was working with Neil Turok at Cambridge on an alternative to inflation, a cyclic model of the universe that replaced the Big Bang singularity with a collision between 2 membranes. The ekpyrotic model, published in Science in 2002, was primarily a solution to the horizon and flatness problems. The dark matter implication emerged as a structural consequence. In braneworld cosmology, our universe is a membrane, a 3-brane, floating in a higher dimensional bulk. Other branes can exist in this bulk simultaneously. They are separated not by spatial distance in any direction we can perceive, but by distance through the bulk. Through the 5th dimension. We cannot see them. Light does not travel through the bulk. Electromagnetic radiation is, like all standard model particles, confined to our brane. Gravity is not confined. Gravitons propagate through the bulk. This means that a matter distribution on an adjacent brane, a shadow brane, would produce a gravitational field that bleeds into our brane. We would detect the gravitational effects without detecting the source. It would be invisible. It would cluster. It would affect the rotation curves of galaxies, the formation of large-scale structure, the distribution of matter at cosmic scales. Dark matter, the anomalous mass that constitutes approximately 27% of the energy budget of the universe, whose detection has eluded every direct detection experiment for 40 years, fits this profile exactly. The Xenon 1T experiment in Gran Sasso, the LUX experiment in South Dakota, the Panda X experiment in the China Jinping Underground Laboratory, none of them have found a dark matter particle. Not a single confirmed direct detection event in the history of the search. The bullet cluster observation in 2006, analyzed by Douglas Clow and collaborators at the University of Arizona in the Astrophysical Journal Letters, showed dark matter separating from ordinary matter during a galactic collision, as if it does not interact with itself. This rules out many particle candidates. It does not rule out gravitational leakage from a brane we cannot reach. If shadow branes are real, the gravitational field holding you to the planet you are standing on is partly generated by matter in a universe you will never observe, cannot communicate with, and have no framework to describe. Number 2. The bulk. Lisa Randall was not expecting to change cosmology when she began her collaboration with Raman Sundram in 1999. She was at MIT working on supersymmetry breaking, a technical problem about why supersymmetric partners of known particles have not been observed at accessible energy scales. Sundram was at Boston University. They were trying to use geometry to solve a mass hierarchy problem in a 5-dimensional model. The result, published in Physical Review Letters in September 1999, is now called the RS2 model, and it is one of the most cited papers in theoretical physics. The proposal, the 5th dimension, is not compactified. It is not small. It is infinite. Our universe is a 3-brane embedded in an infinite 5-dimensional bulk with a specific anti-de Sitter geometry, a warped spacetime that concentrates gravitational fields near the brane and causes them to decay exponentially as you move away from it. Gravity is weak on our brane because the bulk dilutes it. Other particles are confined to the brane. The bulk itself is inaccessible. The model is self-consistent. It correctly predicts Newtonian gravity at large scales. It produces the hierarchy between gravity and other forces without fine-tuning. It makes precise experimental predictions about deviations from the inverse square law at short distances and about graviton resonances that should appear at TV energies. The Large Hadron Collider, during Run 2 between 2015 and 2018, searched for those resonances. None were found in the expected channels. This does not falsify the model. It constrains the mass of the first graviton resonance to above approximately 4 TeV. The LHC cannot reach those energies. A future collider, the proposed Future Circular Collider at CERN, planned for the 2040s, might the bulk. In this model, is not empty. Anti-de Sitter space has a geometry. It has a curvature. There is structure out there, 5-dimensionally adjacent to every point in our universe, separated from us not by distance in any direction we can point, but by a dimension our instruments cannot probe and our bodies cannot enter. The nearest point in the bulk is not far away in any meaningful sense. It is 0 distance from you in 3 spatial dimensions. It is inaccessible. Number 1. Kaluza-Klein's original discovery. In April of 1919, Theodore Kaluza was not a famous physicist. He was an obscure lecturer at the University of Nigsburg working on a relatively peripheral project. He wanted to see what happened to Einstein's field equations if you added 1 extra spatial dimension and then compactified it, rolled it up so small it would be unobservable. He was not expecting to solve anything. He was exploring. The paper he sent to Einstein in April of 1919, addressed directly to him, from a man Einstein had never met, contained a result so unexpected that Einstein sat on it for 2 years before deciding to submit it for publication. The result? When you add 1 compactified spatial dimension to general relativity and then reduce it back to 4 dimensions mathematically. The equations that fall out are not just Einstein's gravitational field equations. They are Einstein's equations plus Maxwell's equations of electromagnetism, automatically, without additional assumptions. The entire electromagnetic field, light, radio waves, the force that governs chemistry, the force responsible for every technology human beings have ever built, appears as a geometric artifact of a dimension we cannot see. No one has explained why this works. It is not a quirk of the algebra. It is a structural fact. Oscar Klein, in 1926, published in Nature the quantist version of the result, giving it its lasting form and providing the estimate that the compactification scale sits near the Planck length, approximately 1. 6 times 10 to the power of negative 35 meters. That estimate remains the standard. Every attempt to extend the result has produced complications. Adding more dimensions to unify the strong and weak nuclear forces along the same lines produces extra fields, scalar fields called dilatons, that should be observable but have not been detected. The original 5-dimensional unification works cleanly. The extended version does not. Einstein knew about this result for the last 36 years of his life. He worked on it intermittently until his death in 1955, never finding the extension he wanted. He published no solution. He offered no resolution. A 1-page calculation by an unknown lecturer in 1919 showed that electromagnetism, the force that holds your atoms together, that drives the signals through your nervous system that allows you to read these words may simply be gravity in a direction you cannot point. And after a century of scrutiny, a century of the most sophisticated mathematics human beings have produced, no one has explained why. Every entry on this list has one thing in common. None of them are anomalies at the fringes of science, at the edges of things we half understand. They sit at the center of our most tested theories. General relativity, quantum field theory, the standard model of particle physics, these are the most precisely verified frameworks in the history of human knowledge. Anomalies should not be appearing here, and yet here they are. Extra dimensions are not a speculation invented to fix a broken theory. They are a mathematical consequence of theories that work almost perfectly. The almost is doing extraordinary work. What this list suggests, collectively, is not that the universe is strange. It is that our dimensional position, inside 3 spatial dimensions and 1 time dimension, is a vantage point so constrained that the machinery generating reality sits directly adjacent to us and remains, by the structure of our physics and our perception, entirely out of reach. We are not confused because the universe is complex. We are confused because we are looking at the shadow of a geometry we cannot enter. If you want to see more videos like this, click the video on screen now.